So Mr. Suhas, basically, I'll just introduce myself. So my name is Parth Joshi.
Hmm?
I am a PhD student in the Department of Mechanical Engineering at IIT Bombay, and
Okay.
so I am actually conducting these live sessions uh,
Huh?
for this particular course. Uh,
Mm-hmm.
so I am basically a recipient of Prime Minister's Research Fellowship, and as a
Hmm.
part of that, I have got an opportunity to conduct these live sessions for this course.
Acha.
So this is the fourth live session,
Hmm.
and so the previous live sessions have happened on every Friday in the previous last few weeks. So
Acha.
so I so I would recommend you to watch those live sessions as well. So they have been uploaded in the YouTube channel for this particular course, which has been created specifically for this course.
Hmm.
So you can find all the recordings of the previous live sessions in addition to whatever lectures and all the assignments that you have. So you also have these live sessions every week. So
Yeah, I also submitted 3 assignments.
yeah,
Okay. Now I am about to submit a fourth assignment,
sure, sure,
mechanical vibration.
sure, sure.
So could you tell me that the link for the YouTube or something like that?
Yeah, I will post that in the chat. So,
Ah.
so basically, whatever live sessions that have happened previously, all
Hmm.
of those will be there in that particular YouTube channel.
Okay.
So you can watch that, watch all those videos over there.
Okay.
Just give me a minute. I will just. I'm just posting a link to the YouTube channel content,
Mm-hmm.
and so you can actually get access to all the videos over there. So
Acha. Acha.
it's posted in the Google Meets chat window.
Yes. Yes.
So so can you just give a brief introduction about yourself?
Sir, I am Dr. Sarjay,
Okay,
a professor in Mechanical Engineering Department. I
okay.
am from JSPM Imperial College of Engineering, Pune.
Acha, okay, okay,
Acha. So I am actually dealing with this subject,
okay,
dynamics of machinery subject.
okay.
Okay, my age is 50 year.
Oh, okay, great.
So I thought that it is better to uh, actually I have prepared the things so properly these things, but not from this point of view.
Okay,
Okay, from examination point of view, but from teaching point of view I have prepared. So
I
here
see.
what I found is that I need to remember some formulas and all that things.
Right.
Okay, some mathematical parts I should know. Then only I should able to solve these assignments and all that. Okay,
Okay, okay,
so just to upgrade my knowledge, you can say.
okay,
Okay, I joined this NPTEL.
okay, great,
Nothing else.
great.
Nothing else.
That's great actually. So you are already a professor, and you have that's great, great to know. So
Yeah,
hopefully this
yeah, yeah.
course is helping you. So I actually in my last
Could you
session, yeah,
could you tell me, sir, in which area you are doing your PhD?
so I am doing my PhD in the area of like system modeling controls in the automotive domain. So I am basically
Acha.
working on electric vehicles, and basically I'm focusing on the controls aspect in particularly with respect to the battery management for electric buses. So
अच्छा अच्छा अच्छा
that is my topic. I myself actually belong to Pune, and
हाँ जोशी पार्क so I wanted to ask you
yes,
earlier.
yes,
Okay, no issue. हाँ
yeah, right,
अच्छा
sure. So that's great. So so actually, so from the teaching point of view, I actually in addition to whatever the regular problem solving and all those things, so I also in my starting from my previous session I had actually introduced MATLAB um, for my like how can we use MATLAB to solve some simple vibration problems, like how that can be
हाँ
used.
हाँ हाँ
So in today's session also I actually have planned to have some more demo on MATLAB. So in previous session, like you can also check uh, the previous session. So it also has some demonstration related to MATLAB. So I think if you can, sir, I think you can consider that as well for wherever, like in your college. So you can actually think of
yeah
including
definitely
that as aspect as well, like using these software tools for
Hmm.
solving some of the vibration problems. So this can be
Hmm.
used for solving problems as well as plotting, analysis, all
Hmm.
different kinds of. It's a very useful tool, and I think, and also all the students would like to see demonstrations on software
Hmm.
tools. So I think that would also be. So I think that would also be something that would
Sir,
be.
may I ask
Yeah.
you some personal question?
Yeah. Yeah. Sure.
Okay, you are from Pune. From which region, sir?
Go through.
Kothurud. अच्छा अच्छा अच्छा. No, actually, I am writing even book also on dynamics of mechanical vibrations.
I see.
Okay, so while writing, actually, I have stuck at one point
Okay.
that I want to generate some numericals.
Okay.
I want to generate new numericals.
I
Okay,
see.
so I want to know that how to generate the numerical basically.
Uh,
Because whatever what we do usually, we take the numericals from some standard books, okay, some
okay.
foreign authors books, okay, and we solve that numericals and the same numericals we put in our books actually. So I
Okay.
don't want to do that. So in that sense, I found SS Rao's book is very good,
Yes. Yes.
Mechanical Vibration by SS Rao. Okay, so I would like to know some how to generate these numericals. So, if you are able to tell me, then it would be better. Or if otherwise, if you ask me to contact someone regarding that, I'm ready to do that one because I want to know that basically.
Sure, sir. So I think we can. I think it's better that we can actually discuss this offline, apart from the meeting. So, sir, I think
Yeah.
maybe you can. Uh, so you can email me on this address. So like maybe we can connect later on uh, after this session.
Session. Okay. No, no issue.
So I am
Definitely.
just posting my email ID over here.
Hmm.
So you can actually just connect over this email ID, and that later on we can discuss more on that.
Okay.
Sure, sir. Then I think we have Prabhu also who has joined. So
Hmm.
welcome. Uh, so Prabhu, I think this is also the first. I think you also I have joined this session for the first time. So let's just let me introduce myself. Uh, so my name is Parth Joshi, and I am a PhD student in the Mechanical Engineering Department at IIT Bombay, and I have been given an opportunity to conduct these live sessions for this course as a part of Prime Minister's Research Fellowship. So that's how I am here, and hopefully, so you are finding these live sessions interesting. Um, so, so Prabhu, can you unmute yourself and just briefly introduce yourself?
Yeah, hello. Can you hear me?
Yeah.
Yeah, okay. I'm an working employee
Okay.
and working in Danfoss Industries.
Danfoss. Okay.
Yeah, basically we are dealing with condensing units.
Sorry.
Condensing units, the outdoor unit.
Condensing units.
Yeah.
Okay. Okay. Okay.
So and then we are facing a lot of issues in the vibration.
I see.
So I'm a design engineer and I would like to understand how can eliminate vibration in our
Sure.
units.
Sure. So your background is like engineering, like in what discipline have you graduated?
Yeah, I'm a mechanical engineer.
Mechanical. Okay.
Yeah,
Fine. Sure. So so your motivation for the course is to apply things in the industry.
exactly. Yes.
Okay, fine. So so far, so have you got a chance to attend the earlier live sessions and or watch the recordings?
Uh, yes, sir. Basically, I have tried to attend the live interactions, but since it is on Friday, I couldn't able to attend these sessions. So today
Okay.
I got some free time, so I thought to join.
Sure. So you can
Yeah.
always go back and watch the recorded session. So this session is also being recorded right now,
Mhm.
and so you can watch this recording later. So I have already posted the link to my YouTube channel. So it will be uploaded every week over there. So
Okay.
you can have a look at the earlier sessions. So in the previous sessions, I have actually tried to solve some typical problems which you would see in the assignments mainly. So my initial motivation was to address if there are any questions, specific questions or queries related to the course content, assignments, or anything in general, or and then also to solve some demonstrate some typical examples that you would encounter in the the kind of problems you would see in assignments. And then I also tried to give you a demo on MATLAB, so which is a useful software tool which you can actually use it for even for solving some simple vibration problems. So in today's session, I also plan to cover some basic solution how to solve a vibration problem. In today's session, I am actually planning to cover how to solve a differential equation. Like, so you will get an equation of motion in the vibration problem. So uh, so how to solve that equation of motion using numerical techniques. So hello, so Advait Pranshpe has also joined us. So welcome Advait. Uh, yeah, so so I was saying that so I have actually I am also trying to bring in some component of MATLAB which in general interest, like it's not part of the course or anything, course syllabus or course deliverable, anything like that, but just for general interest, and it will be a useful tool to learn and apply in any problem. So I think Prabhu, you might be also using MATLAB in your company, right?
Yes.
So you're already familiar with MATLAB?
Not up to some expert level, but
Sure.
basic. Yeah.
Yeah, sure, sure. Yeah, so Advait Paranspe, so can you just quickly, if you could unmute yourself and just speak and just give you a brief introduction about yourself. Advait?
Hello, sir. Am I audible?
Yes, yes. Yeah, please go ahead.
So actually, sir, my name is Advait Paransh. I'm from Pune.
Yeah.
So I'm currently in third year mechanical engineering
Okay.
in MIT WPU.
Okay.
Yes, I'm currently doing the course of Introduction to the Vibration.
Yeah, great. So what's your motivation to take this course?
Yes, actually, in our curriculum, this subject is not included as such yet. So I
Okay.
thought to cover this as well, since the mechanical engineers also need to learn this in deep as well. So that's why I selected this subject.
Right, right. That's great. So we have a nice mix of participants. So Professor like Suhas Sarji, who is a professor, and Prabhu, who is in industry, and Advait is a current engineering student. So that's great. So I think hopefully all of you would find something useful in this course. So I think let's get started with this session. So yeah, so before that, so is there any quick feedback or any question, specific question for me? So if any one of you have watched the earlier live sessions already, so if you have any feedback.
Uh, 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 Regarding previous previous sessions or the or
Yeah, whatever,
what?
like in general, about the course,
Okay,
about the
okay.
live sessions or
So
previous.
I haven't attended your previous sessions. Okay,
Okay.
so I'm not able to give the feedback for that.
Sure, sure.
Okay.
Sure, sir.
So
So
now, so today I was solving an assignment,
okay.
assignment number 4. So in that assignment number 4, some eighth problem numerical,
Okay.
I was not able to properly
Okay.
solve that.
Okay.
So if you do that one, it would be nice for us.
Okay.
Ah.
So assignment number for question number 8. So what was the
Yeah.
doubt that you had?
Doubt means I didn't get the answer of that actually. I tried my level best to
Okay.
get the answer. Okay. But I didn't get the answer of that.
Okay, sir. So I think I'll just look into that and maybe get back to you later.
Acha.
Anyone else has any question? So I'll just start sharing my screen. So in today's session, I actually have planned to solve some simple problems related to this week's course content. So so I have selected some problems which are similar to the kind of questions that you will see in the assignments, and then I think you would hopefully this will help you to solve the assignment questions. So let's get started. So the first question is about, so when there is a shaking force that is transmitted through the spring, so let us say there is some machine and there is some shaking force that is being transmitted through the spring to the foundation. So the question asks, like, so when does the damping become detrimental? So it asks about, this question is basically related to force or motion transmissibility. So uh, anyone has any idea about this question?
Hello.
Yeah.
I got the answer root 2.
Okay. Okay, sir.
Ah.
So your answer is root two, right? So how can you explain to us like how does that? Uh,
No, not it. It is not possible now. Okay. The formula I have used, I think, no, that transmissibility ratio and all that. Okay.
right.
So then we have substituted the value, and
Okay.
finally I got this root 2 value.
Okay. So how like how what was the basic logic that you had applied, sir?
That transmissibility ratio is there. Now, shaking force is transmitted
Right.
through the spring damping becomes okay.
Yes.
So transmissibility ratio is equals to that FT upon F naught, something like that. No?
Correct.
FTR. F naught.
Right,
Is equals to under root 1 minus, that formula is there.
right. Yeah, there is a
1
big
minus.
expression. Yeah, right.
Yeah, big equation is
You are right, sir. So right.
there.
So so basically the force transmitted to the force applied. So that ratio, if you consider that. So so basically this is the equation for the transmissibility. Now if you plot this equation, so with respect to uh, the basically the transmissibility with respect to uh, uh, basically with respect to the frequency ratio of frequency omega by omega n, which is r, and here this is basically the transmissibility ratio. So 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 if there will be certain trend like this, like let us say the system is under damped, it will be, and there will be like depending on the level of damping that we have. So there is a certain kind of a trend. So like if we now have different levels of damping, so this is how the curves would look. So let us say this is zeta 1 corresponding to zeta 1, zeta 2, and this is let us say for zeta 3. So so now at some point there is a crossover that happens. So and this transmissibility ratio, its value is actually 1 at some, let us say some r naught. So what is the value of r naught, and what is the relation between zeta 1, zeta 2, zeta 3? So if we have want to uh, arrange them in if we can if you want to arrange this in an ascending or descending order, so what would be the order? Anyone has any idea what would be the order in which? Any guesses? So if we basically if we substitute, if r naught is root 2, so then that is the point at which the transmissibility ratio is exactly 1. So for irrespective of any damping value, the transmissibility ratio will be always 1. Now if r is greater than root 2, then the transmissibility ratio is always less than 1. But now here there is a trend reversal. So so if we see that, so then uh, whatever the trend with respect to zeta 1, zeta 2, zeta 3 is there for transmissibility ratio before r is less than r naught, there is a reversal in the trend. So here zeta 1 will be less than zeta 2 is less than zeta 3. So as we increase the damping, the transmissibility ratio actually decreases, right? So for this earlier, so when r naught when r is less than r naught, then the transmissibility ratio decreases with increasing damping. On the other hand, the uh, when the frequency ratio increases beyond root 2, then as we increase the damping, so basically if there is an increasing damping, there is a increase in transmissibility ratio. So that is the region where damping actually becomes detrimental. So by actually increasing the amount of damping in the system, that will actually cause an increase in the transmissibility ratio. So more forces will be transmitted to the base, or whatever, like, or from the base to the machine, so which is not desirable. So that is the, so this is basically the more detailed actual plot of the transmissibility ratio here. So we observe that, so as we basically increase damping, so when r is greater than the square root of 2, then the transmissibility ratio increases with increasing damping. So the correct answer is root 2. Any questions?
No.
Sure. Yeah, so then we come to the next question. So this question is again based on the same concept. So it asks about displacement transmissibility for so for all values of damping ratio. So when we put basically r is equal to root 2, so let us write, let us verify this. So when we put r is equal to root 2, so then we get into r square, which is root 2, which is 2 into 2 upon 1 minus r square, which is 2 the whole square, plus 4 zeta square into r square, which is again 2. So the numerator is 1 plus 8 zeta square, and 1 minus 2 is again 1, so whole square. So the numerator and denominator are equal. So basically we get the value of displacement transmissibility is 1 for r is equal to root 2. So which is what we had expected. So we just saw this in the previous question. So when r is equal to root 2, the transmissibility ratio is 1. So let us move on to the next question. So there is a vibrating machine which is there is some isolation which is used to isolate it from the floor using springs. So it is given that the ratio of the excitation frequency to the natural frequency, that is equal to 0.5. So r is equal to 0.5, and it asks about the transmissibility ratio. So again we have the same concept here, but now there is nothing mentioned about damping, and r is actually less than root 2, it's not equal to root 2. So then let us assume that, because nothing is given, we will assume the damping to be 0, because it is not given. Then so let us again substitute. So when zeta is equal to 0, so this expression will just become mod of 1 upon 1 minus r square. which is 1 upon 1 minus r square, which is 1 by 4, so it will be 4 by 3, which is 1.33. So the correct answer to this question is D. So any doubts?
No, sir, no.
Okay. So now we now come to a different concept of Coulomb damping. So that was also discussed in this week's lectures. So now here it asks uh, by what extent is the amplitude of the motion reduced in each cycle. So let us say if we have a simple spring mass system, here the mass is fixed to the wall, and let us say this floor, it has a coefficient of friction mu. So then if we let us say if we denote, if we just draw the free body diagram of this mass, so then there will be a spring force acting, then there will be the weight, let us say W, and there will be some normal reaction, and let us say if the velocity is in this direction, then the friction force will be, let us say, in this. So let us say Ff is the friction force and Fs is the spring force. So this is the free body diagram of this mass. So now so the friction force would be what? Since the block is sliding, it will be the coefficient of friction into the normal reaction. So that will be the magnitude of the friction force. Now in terms of this friction force, what would be the reduction in the amplitude of the motion when it is, let us say if this now mass is subjected to some force, let us say Ft, which is, let us say, some F naught cos omega t. Then if we want to determine what by what and so forget about the forcing. Let us say if we give it some initial displacement, let us say some initial displacement x naught, and then leave it to oscillate freely, then what would be the amount by which the amplitude is reduced? So that is what is asked. So how would we solve this problem? So anyone has any idea?
No, sir.
Okay. Yeah, so basically the friction force over here will change direction depending on the direction of velocity. So when, let us say, the mass is moving between, let us say, two extreme positions. So let us say this one like is the extreme position 1 and 2 are, and let us say this is the equilibrium position. So then so when let us say if we give it an initial displacement, let us say here if we start from 2 and then let the mass go, so then first it will go from 2 to 1, so there x dot will be less than 0, because let us say we assume these kind of like axis xy, where the right hand side is like the velocity pointing towards right is positive and towards the left is negative. So then x dot would be 0. So then the friction force would act like this. So when the velocity is like this, the friction force would be acting like this, and when x dot is positive, it is acting in this direction, then the friction force would be uh, in this direction. So the direction of the friction force will change depending on the direction of the velocity. So then if let us say if the friction force was not there, we generally use we just apply the Newton's second law to the system for deriving the equation of motion. So similarly, if we do like that, so here we will have to consider each uh, half of the motion separately, because the direction of the friction force will change depending on the direction of the velocity. So here this slide shows the same figures like what I just had shown. So let us say when so for when the condition when the velocity is positive, so let us say this is x dot is greater than 0, so this is for that case when x dot is greater than 0, and this is the case when x dot is less than 0. So the free body diagrams are here, and so we can, using this we can write the equation of motion. So these are the equations of motion. So they will be changing depending on the direction of the friction force. So either it would be like this, where the right hand side has minus mu n, or plus mu n if it is acting in the opposite direction. So basically this is a non-homogeneous second order ordinary differential equation. So how would we solve this kind of a differential equation? We will basically have two parts of the solution. One would be the complementary function and the particular integral. So for this type of uh, problem, so we will have this first usual part of like a sinusoidal nature, as we have when, if let us say this right hand side was 0, and then this is basically the particular solution depending on the direction of the friction. So we will have two kinds of response, like either this one or this one, depending on the uh, direction of the friction force. So now depending on the initial conditions that we apply, so we would have to solve this equation for the first half cycle separately, and on the second half cycle separately. So let us say if we have let us look at the first half cycle. So if we give an initial displacement x not greater than 0, so then the velocity, so it would have 0 initial velocity, but then it will gain velocity in the left direction. So then we will have to refer to this part. So we will have to find basically A3 and A4, and using the initial conditions, and then so when the mass reaches the other extreme position, whatever is the uh, displacement of that of the mass in that extreme position, so that we will substitute as an initial condition in the other second half. So basically what I mean to say is, so we will evaluate A3 and A4. Basically x dot, basically we know that x dot of 0 is 0, and we know x0 is x naught. So then we can find out A3 and A4. So that will be basically x naught uh, so it will be basically x naught is equal to a3 plus mu n by k, and if we differentiate this, it will be basically omega a4 is 0, so a4 will be basically 0, and a3 we can calculate from this, and then uh, so when it will when the mass reaches the other end of the other end of the extreme position, so we will get uh, the other basically at, so when time, so, so for the first half cycle, so the time would be half of the time period, so half of 2 pi by omega n, so basically it is pi by omega n. So when the time is pi by omega n, so we will substitute the value of this in that, so so we will get so x naught minus mu n by k, so cos omega n t would be minus 1 at t is equal to pi by omega n, and sin omega t will be obviously 0, so plus mu n by k, so that will be the displacement uh, of the mass at the other, so let us call it as x1, let us say, so after x like first half cycle, let us say it's half, so that will be, so x half would be minus of x naught minus 2 mu n by k. So from x, so basically it has reduced by 2 mu n by k in one half cycle. So similarly in the other half cycle, we will assume this as the initial condition as minus 2 mu x naught minus 2 mu n by k. So we will give this as the initial condition. So the velocity will be 0 at the extreme position. So this we will give as the initial condition, and then use this particular differential equation which is shown over here, and so we will put this as the initial condition, and then again get the values of a1 and a2. So if we put the initial condition, yeah, sorry, I think my screen share went off, so let me just get it back. Yeah, so basically we got the x half is x naught minus of x naught minus 2 mu n by k, and so that will be basically the x of t is equal to pi by omega n, and so we have to basically find out now what is x at t is equal to 2 pi by omega n. So that if we actually proceed using the same approach, uh, so that we will uh, get it as x naught minus 4 4 mu n by k. So the amplitude, so we started off with x naught and it got reduced by minus 4 mu n, so 4 mu n by k. So basically the amplitude reduction in one cycle is equal to 4 mu n by k. So if we try to plot the response, so if we solve the differential equation for each half separately and then if we try to plot the response, this is how it will look like. So as I just told you, so we derived up to this point, and similarly if we proceed then we will get this as after one cycle. So therefore the reduction in amplitude is 4 mu n by k. So now I have put up another example. So I have planned to actually show a small demo on how do we use MATLAB to solve these some of the equations of motion in a vibration problem. So let us consider this simple problem. So if we have a simple spring mass system, so let us just draw the same diagram. So it is same, and let us say this is subjected to some forcing which is f naught sin omega t. So f naught is given, omega is also given, and we also know the initial conditions. We know the mass, we know the stiffness, and we also know the coefficient of friction mu. So now so we will just quickly look at how do we now use MATLAB to plot basically the response to this forced vibration, and see how to solve the basically the differential equations that we would get. So as we just saw, we get the two different equations. So if we can just write the differential equation, so it is either plus or minus mu n depending on the direction of the friction force along with the f of ft. So so we can actually write mx double dot plus kx plus, so if we basically write normal reaction is mg, so mu mg into sine of x dot, so is equal to f of t. So sine of x dot, so whenever, so when the, it should actually be minus this. So when the sine of x dot is positive, the friction force will be negative. It will point in the opposite direction, and similarly when x dot is negative, the friction force will be positive. So the sine of x dot is basically the signum function. So it basically be it and it basically checks what is the sign of the velocity. So now this is now a non-linear differential equation, and so we will have to use some. It is difficult to solve this analytically, so then we will have to use. We generally we can use numerical techniques in MATLAB to solve these kind of differential equations. So we will just quickly see how to use MATLAB now. So any questions till now?
No.
So I'll just share my screen. So can you just confirm whether you are able to see my screen?
No, I am not able to see. Now it is okay.
Yeah. So so are you able to see the MATLAB window? I'm showing the MATLAB code.
MATLAB 4. Yeah, able.
Okay. So so this basically is the MATLAB code if you want to solve this differential equation using some numerical solvers that are available in MATLAB. So for that we have to first define basically the initial conditions that have been given. So we define an array x naught which contains the value of the initial displacement and initial velocity, and then the time span over which we want to see the solution of the differential equation. So let us say we want to, in this case let us say we want to just see the solution over the first 5 seconds and with a time step of 0.01 seconds. So now here in the line number 12 which I am pointing to right now, so this is the ODE 23. This line is for that ODE 23 solver, which is again a solver in MATLAB for solving these non-linear kind of differential equations. So for that we have to first provide an input to this. So the first we have to write a function which describes the differential equation in a state space format, and then we have to give the time span as the input and the initial condition. Similarly, there is another solver ODE 45, and here also we have to give the function handle as the input and then the time span and the initial condition, and this part of the code is plots the basically the response as a function of time. So let us just first run and see what is the output of this code. Yeah, so we see this kind of a response. So so here we see that there is some small difference in the results that we get with ODE 23 and ODE 45 solvers. So they are depending on the characteristics of the problem and the differential equation and the numerical technique. So there will be some small differences in the solution that we get, but more or less it's the same behavior. So in the steady state, so beyond around 3 seconds or so, this is still is settling down to its steady state. So then we see more or less constant amplitude oscillations beyond 3 seconds. So up to 3 seconds we see there are some transient transients because of the presence of the free vibration component in the total response. So So basically this is the output of this code. So as I mentioned, so we need to provide this kind of a function as an input uh, to this code. So in this we have to give the differential equation in a state space form. uh, so here the input is basically uh, the time, and the x is basically the displacement and velocity vector. So combined, so x contains basically the displacement and velocity as in a vector form, and y is basically the right hand side of the differential equation. So in the state space form, so y is again a column vector. So this is the way in which we need to provide the function, and then we just put it into this non-linear. So we provide this function to this solver. This is how we get the numerical solution to the differential equation. So I'll just quickly show what exactly I meant by state space form. So let me so we saw this differential equation, it is in this form. So now to solve this differential equation, so basically we have mx double dot plus kx minus mu mg into sin of h dot is equal to f naught cos omega t. So now if we want to write this differential equation, so we have this, let us say for the purpose of the solver, so let us say this is the x is the column vector that we need to provide as the input. So let us say it has two values, x1 and x2. So here x1 is basically the x value, which is basically the displacement, and x1 dot will be x dot, so that we call it as x2. So x2 is basically the value of velocity. So this is basically displacement and velocity. x1 is displacement and x2 is velocity. So now, so x2 dot, so what will be x2 dot? It will be x double dot. So now we have to write the expression for x double dot. So x2 dot will be x double dot, which is basically f naught by n cos omega t minus k by m into x. So if we write x as now x1 plus mu into g into sin of x dot, or x dot is basically x2. And we have this x1 dot is x2. So we have this differential equation. So x1 dot and x2 dot, so that will be basically x dot. So we have to So we have to write x dot as a function of x and t. So this is the general state space kind of form that you have to have, and this function f has to be provided to f is basically the input to the solver in MATLAB. So this is how you can use MATLAB to solve this some simple vibration problems. And basically this not necessarily vibration problems, this can be actually, these non-linear solvers can be used to solve any kind of differential equation in any domain. So this was about using MATLAB. So that's all that I had from my end for today's session.
Thank you, sir.
So is there
Okay.
any specific doubt or any question or any feedback?
No, question was not there. This MATLAB actually, don't use these things. Actually, I know that it is useful.
Yeah,
Okay, but um, otherwise, the things are very nice. Uh, the way you handle these, actually, these are the equations and all that things. No, so it is very nice actually.
sure, thank you.
Okay, I understood that. Fortunately, I am also dealing with this subject, so I understood the things. So really, it has some depth actually. Okay, and thank you for the same.
Sure sir,
Thank you.
thank you very much.
Hmm? Okay, thank you, and I will contact you through mail. Okay.
Sure sir, yeah, I think maybe we can discuss that regarding your question. um, so you can like you can please write to me on this email ID.
Yeah.
Sure sir, thank you very much for joining this session. And so
Thank you, sir.
please do
Thank you.
also watch all the other earlier live sessions, and like we will have these live sessions every week, every Friday, between 6 to 7 in the evening. So please do join, and let me know your feedback as well on whatever the earlier live sessions were. So
Definitely,
so
definitely,
I can
definitely, definitely,
use, like, incorporate your whatever feedback in the future sessions.
definitely, sir.
Sure.
Definitely.
Thank
Hmm?
you very much.
Thank you. Thank you once
Bye
again.
bye.
Okay.